Last example is in a more complicated model. So now I'm not using anymore a statistical model for the dynamics. Now I'm using a differential equation. So this is a work of Denis Dreano in Coast. It was during his thesis. So basically, he was trying to monitor the blooms. So the blooms are a kind of emergence of algae in the water, and it can be a disaster, especially in the Red Sea. And so to monitor these blooms, they use satellite observation, so chlorophyll satellite images or color images. And also they use a quite simple one-dimensional model. It's in 1 pixel, I will say, but with different depths. So you have like 80 variables at different depths. So this is the result of EM. So you can see here the likelihood, which is increasing. So here I show the error of the satellite observation. So basically, I didn't check with the error given by the producers of chlorophyll data. What is nice, and I would like to focus on that, is that we have an estimate error of the dynamical model. So in this case, it is a simple with 80 variables model, and we know that the model is not good enough. And here we have an estimate of the error. So basically, I show you at the surface the variable at the surface and at a given depth. So this is a mixed layer depth, and you see the Q estimates of the different variables. So what is nice, I will focus on that, is that you can see that there are groups of variables which are positively or negatively correlated. So the error are positively or negatively correlated. And I think so this information can be also good for the people who are working on the model, directly on the model. It can give a crucial information about where the model is good and where it is not. And this simple machinery, I will say, is able to highlight some places in the model where there are correlated errors. Okay, so these are quite simple example. I have also some examples in chaotic models. I don't show that. You can find this if you are interested. You can find this on my GitHub page. So the code is CEDA for covariance estimation in data assimilation. And if you want to play with the Lorentz 63 and Lorentz 98, you can play and try to see the estimation of Q and R in these different chaotic models. It's very easy to put your own model and your own observation on this code. So if you are interested, you can use and put directly your model and your observation and try to see the estimation of the error of the model and observation. So this is, I think, for the people from IKES at the RIKEN, we can also test in your different problems in June and July. Anyway, so the conclusion of this work is that I hope with the first slide you you think now that estimate Q and R is very important in data assimilation. So for the people who are doing Kalman, they know that. But for the other, I hope I was clear enough. So it's important, yes, because if I come back to my first experiments using a univariate model, if your spread, if the estimation of your uncertainty is badly scaled in data assimilation, it can be a real problem. For instance, if you are doing some projection for the future, for instance, in climate sciences, this is very important. So I think this is crucial, and so I will say that yes. So this presentation is a part of a review paper I'm preparing. So I try to compare the four methods I explained before. So now the perspectives. So I think I didn't talk about this, but for the four methods, they are offline. Some of them are offline, and some of them are online. So basically, offline methods are quite robust. For instance, the EM estimation is very robust, but it's offline. So we need a batch of observation, and on this observation, we do some iteration, and we estimate Q and R for this observation. So it is good to use offline method just to calibrate and to see what is a global form of Q and R. So this is, I think, important. And then I think we can use online adaptative estimation, and adaptative in the sense that Q and R can vary in time. Possible extension. I talk about this in the EM algorithm, is that we can estimate the initial condition. So this is a background in data assimilation. It's the X at time 0, so the state of the system at the first time, and it is very easy to incorporate this information and try to estimate that, for instance, in the EM algorithm. And so a natural extension of that is also to, no, it's not what I want to say. We can also estimate, for instance, the bias in the model and also in the observation. So this is also a possibility. So because sometimes model have systematic bias, observation also, and here we can propose to estimate the bias. Okay, so these are ongoing works on this main topic. Currently, we submitted an article just last week on using the EM algorithm, using the conditional particle filter and smoother. So it seems to be very efficient. So not in high-dimensional problem, but it's still reasonable for a problem with less than 100, where the state of the system is close to 100. And also, we can combine the estimation of Q and R in different data-driven approaches. So this is for the guys, for you, what I have presented on Friday. So if you remember, if I use analog data assimilation, so basically it's a data assimilation where we use the analog forecasting to reconstruct the model. So in this case, we can also use the estimation of Q and R, and it seems to be very efficient. So we are currently working on that. Okay, so it's finished for me. I just would like to show you my campus. So this is my campus. So it's in Brest. It's in the northwest of France. and it's open to the Atlantic Ocean. So if you want to, I don't know, if you want to come and to work with me and to visit our place, you are welcome. Thank you very much.
Questions or comments?
Yeah.
You mentioned online algorithms. So I wanted to make sure I understand. So if suppose Q and R are not evolving in time, when you do EM, you have to sort of collect all the data and then you run the EM iterations. And then if you have a new piece of data come in,
do it again.
Start from the beginning in some sense. Or is there an online EM algorithm?
There is some online EM. You're right. So there is a paper of the French guy in London. So they use online EM. So they try to approximate the likelihood function at every time t, and then to maximize this likelihood. So this is, you are right. This is a perspective. Try to apply online EM to estimate adaptive Q and R matrices. Yeah, completely.
The other question is on parameterization. So Q and R become very two-dimensional. What are the common choices of parameterization?
I think the classical one are parameterization on the diagonal. So the same error in all the state, or different errors at different depths, for instance, and location. And also the correlation length. We use a very simple. If you know spatial statistics, we use Gaussian correlation, decreasing correlation. So it seems to be quite reasonable. Because if I didn't show that, but if I apply this to a dynamical model, so we use in data assimilation, like shallow water model, for instance, we see if we estimate the full Q matrix, you see this kind of correlation length. So we can assume that it's reasonable to put, to impose that.
Thank you very much for your interesting talk. I'm working on the information issue of our global data assimilation system, and now I'm using the innovation statistics for not for background error covariance, but for analysis error covariance. And
for analysis error covariance
using DeRogier's innovation statistics.
Okay.
And I have two questions. And the first one is, can we estimate the analysis error variance using your Bayesian and like a maximization of likelihood method?
You mean the analysis covariance error?
Analysis error variance.
So this is directly given by your Kalman, no?
Yeah, but sometimes if the Q is imperfect, the analysis error variance is also can be underestimated.
Yes, so this is it's exactly what I have shown at the beginning. You know, the confidence interval. This is your analysis covariance error. That's it. So if we use a bad Q, so you will have underestimate or overestimated PA. Okay. So yes, you need definitely to use this kind of method.
Yes, I see. Okay.
Because if you are able to estimate the good Q, you will have the good PA.
I see.
PA is analysis covariance.
Okay, and my second one is, have you ever compared the four methods in terms of the estimation accuracy of the covariance of the Q and R?
Yeah. It's not in this presentation because it's still a work in progress.
Yeah.
So sorry for that, but so I implemented three of the four methods, and so I have some results for these three methods, but not the last one, and not the Bayesian one. And so I didn't want to make the comparison just on 3 methods. But what I can say is that in my experience, I will say that the last one, the EM algorithm, is extremely robust, and it's a lot of computational time because you have to apply the filter and the smoother during different iteration. But I will say that it is very robust. On the other methods, they are online methods, so they are very they depend on tuning parameters, and they are extremely depending on these tuning parameters. I didn't talk about this, but you have to. I did a lot of experiment, and the results are very unstable using the other method. So except the inflation method is quite robust, I will say. But in the inflation method, you are not estimating Q, so you are estimating an inflation factor. So, I mean, this is good if you are doing some operational data assimilation. I know that we cannot estimate all the Q error covariance, so it's very convenient to estimate only a scalar an inflation factor. But if you want to know where is the error of your model and where are systematic errors in your model, at a given time you have to estimate Q, and it's very difficult, I think, using the innovation statistics in the observation space. I don't know, Takemasa, because you estimate the inflation factor, and do you think it's possible to, did you try to estimate directly the Q matrix instead? No? Okay. Wow.
We assume that there is no Q.
Yeah, you assume in this case that there is no Q, but
No random process.
yeah. But increasing PF, it's like assuming that some.
So we have different sources of. I mean, we have different. So in addition to Q, we have other reasons why we underestimate P.
Okay.
So that's why we need the inflation, even if we have proper Q.
Okay.
So I think we need to discuss that part.
Okay.
Yeah, to clear up.
Yeah. Okay.
Okay, so it's coffee break. Yeah, thank you very much.
Thank you.